Hi, I'm Jordi, a computer science and applied mathematics engineering student. I took part in the press summer of HPC 2019, and for 2 months I have worked on a distributed memory Radix sort. Quick sort, merge sort, insertion sort. We can quote many sorting algorithms, but why? Why are there so many? Did you know that your computer spends more than a quarter of its using time to sort numbers and data, according to Donald Knuth? This is why they are important. The statistic is maybe a bit old, but for several specialists, it is still the case nowadays. The Radix sort is most probably the faster of them, even faster than the famous quicksort because it can run in big O of n, contrary to big O of n log n for the quicksort. How does it work? Let's see an example. We want to sort this small list. First, the Radix sort uses the bitwise representation of the numbers as they are stored in a computer. The algorithm iterates through the number of digits of the numbers. This is the D parameter, D for digit. Here, the biggest number of digits is 2, therefore D equals 2. This is the Radix sort algorithm. For each digit, I, where I varies from the least significant digit to the most significant digit, use counting sort or bucket sort to sort the numbers according to the highest digit. Let's apply this to our list. This is the bucket sort according to the least significant digit, and we can notice that the list is still not sorted after. We have not finished the algorithm yet. We repeat the same with the next digit, which is the last in this case, the most significant digit. Once done, everything is good. The list is now sorted. The complexity is big O of n because we simply call D times the bucket or counting sort, and both run in big O of n in this configuration. What if we want to sort a huge amount of data? They can be too huge to be stored on one single computer, or the execution time can be too long. This is where HPC and parallelization come into play. Let's define properly our problem. We have P processors able to communicate using MPI, and each of them has a unique rank. Our data are distributed equally across the processors, and they are too huge to be stored by one single processor. We want to sort them in a distributed way. After the sort, the processor 0 should have the lower part of the sorted data, the processor 1 should have the next, and so on. Okay, now let's see my solution. For each digit, still from the MSD to the LSD, we first sort locally the data on each processor according to the current digit and using the bucket or counting sort. Then we compute which processors have to send which portion of the local data to which other processors in order to have the distributed list sorted across the processors and according to the current digit. We still have one iteration to do in our example. And now our distributed array is sorted like we want.